Hello everyone. Before starting the lesson, try this warm-up. F of x equals sine x is shown. Do the following transformations. There's 3 of them. A vertical stretch times 2, a horizontal compression times 2/3, and translated right 60 units. You might need some graph paper for this, but copy this function and then try to perform these 3 transformations and then check back in to see how you did. Well, this is what you should get. Let me explain. If I start with this point right here, and I do a vertical stretch times 2, I'm multiplying the y value by 2. Well, right here, the y value is -1. Times 2 would be -2 down here. Then I have to do a horizontal compression times 2/3. Horizontal is your x values. So I'm going to multiply my x values by 2/3. Well, 2/3 of -90 is -60. And then translate right 60 units. Well, that would be over here. So this point transforms into this point down here. We can do the same thing with the next point. So here's a point. Vertical stretch times 2. Well, vertically, it's at 0. Times 2, it's still 0. Horizontal compression times 2/3. So its x value here is 0. Times 2/3, still 0. So then we translate right 60 units over here. So this point transforms into this point. If you follow the same process, this point transforms into this point. This one actually ends up staying where it is. This point transforms into this point, and this point transforms into this point. If you had trouble with that, then you should reach out for some help before you continue on the lesson. Because we are talking about transformations in this lesson. Transformations of sinusoidal functions. So we're going to determine how transformations affect the parent function f of x equals sine x. Now just remember, transformations are changes made to the parent function. So if you change the equation, you're going to have a corresponding change in the graph. The location of where you change the equation makes different changes on the graph. And you've seen this before earlier in the unit. We're just applying the a, k, d, and c values to sine functions now. But a still represents vertical reflections, stretches, and compressions. K still represents horizontal reflections, stretches, and compressions. D represents your horizontal translations, left or right, and C represents your vertical translations, up or down. So all these values still mean the same thing, it's just we're starting with a different parent function. Now, when I took up the warm-up, I showed you how we graphed from transformations in previous units. To make a graph from an equation, we usually graph the parent function, list the transformations, that was all given in the warm-up, and apply all transformations to a few points on the parent function. That's what I did when I took up the warm-up. However, it can be tricky to do that with sinusoidal functions, so we will graph them a little differently. So in this lesson, I'm going to show you another way that we can graph sinusoidal functions. And a lot of people find that this makes a little more sense than the transformations that I did in the warm-up. So you just have another tool in your toolbox if you're asked to graph a sinusoidal function. So this graphing method I'm going to show you is, I call it the box method. I don't know what other people call this. First off, draw a box. Here's a box. And you should draw in these dotted lines as well. So this will make up the box. Next, label the axis, the maximum, and the minimum. Those are all on your y-axis. Now I'm going to show you how this works for the parent function, f of x equals sine x. The central axis is at y equals 0. The maximum value is 1, and the minimum value is -1. So That's how I label this side of the box. Next, label the beginning and end of one period. Well, for the parent function, the start of my function is at 0. I know the period is 360, so I'm going to end at 360. Now, at this point, it's probably a good idea to label these lines as well. If you're starting at 0 and you're ending at 360, halfway in between those two values is 180. If you want to label this, it would be halfway between 0 and 180, so that's 90. And for this one, it's halfway between 180 and 360. That would be 270. Next step, sketch the sine curve in the box. So I know my curve is going to start on the central axis. It's going to go up to the maximum, then back down to the central axis, then down to the minimum, and then back up to the central axis. So this is what one cycle of the function would look like. It goes up, then back down, then back up again. So now that we've figured out this box, the last step is to actually make a graph. You take the values you figured out here and you copy the box onto the graph for the desired number of cycles. So I have figured out where these points are, so whatever the scale on the graph is, you can figure out where to plot your points. And then it's a lot easier to draw the curve. You don't have to perform transformations on every single point on the curve. You can just copy and paste your one cycle onto your graph. Now this will change, your numbers will change, and maybe your drawing will be a little bit different. It might go down instead of up at the beginning, depending on what your equation is. But this method will always work for finding what values you should put on your graph. Draw the central axis, the maximum, the minimum, the starting point, the ending point, and which direction your curve opens based on the equation. So here's an example. This is the box that I drew for the parent function, and we're just going to use this as a basis for how we would draw this function. G of x is equal to negative sine x. So what's different about the function compared to the parent function? Well, just this negative sign. So if we think in terms of transformations, all we've done is we've put in a vertical reflection. We haven't moved the function up or down because I don't see a c value over here, so the central axis is still the same. The amplitude is unchanged because there's no stretch here. So my maximum and my minimum values are still 1 away from this central axis. My starting point is still 0 because I haven't moved this function left or right. And the period remains unchanged because there's no horizontal stretches or compressions. So I'm still starting at 0 and ending at 360. So what is different? Well, we have a vertical reflection. So instead of going up, then down, it goes down, then up. That's a vertical reflection. And now I could take all these points that I figured out and I could draw this onto my actual graph, and then I would have a nice graph of this function. Okay, let's try this function. Here I have an a value of 2. So let's start with the central axis. Has it changed from the parent function? No, because there's no c value. That means the central axis has not shifted up or down. The amplitude will be different though, because we have this vertical stretch times 2. So that just means our amplitude is going to be 2 instead of 1. That's what a vertical stretch does. It changes the amplitude on these functions. Now what about the starting value? We don't have a translation left or right. There's no d value in this equation, so we're still starting at 0. And the period is still 360 because we don't have a k value, which would indicate a horizontal stretch or compression. That would change the period. So we still start at 0 and end at 360. Now what about the shape of the curve? Is it the same or is it going the other way? Well, do we see a vertical reflection? No, because a value is positive. So we still end up with the same shape and direction of opening. So now we've figured out that we're going to have a different maximum and minimum value, but our starting and ending points will stay the same. But this will change how the graph looks. It'll be vertically stretched. It'll just go up higher when we graph this. Now this function is -2 sine x. So I want you to pause the video and see how you would complete the box drawing. So try it on your own and then check back in to see how you did. So this is a combination of the last two examples. We have a vertical reflection, which means our curve is going to go down at the start instead of up. We also have a vertical stretch, which means our amplitude is going to be 2 instead of 1. Other than that, these values stay the same. So this would be the box drawing for this function. Now here's one that's a little bit different. Here we have a 2 inserted in this position. Now I just want to remind you, this is on your help sheet to help you locating where the numbers are in the transformation order. This 2 is in front of the x, but it's inside the sign. So inside the sign part, in front of the x, that's a k value. So if you look at your help sheet, it says k values deal with horizontal reflections or stretches and compressions. But you're multiplying by 1 over k. So if k is 2, you're multiplying by 1 over 2. Multiplying by 1 over 2, you're going to get a smaller value. That means you're compressing your horizontal values. Another way you can think of this is that one complete cycle is going to take half as much space. So instead of taking a full 360 degrees, it's going to take half as much space, 180 degrees. Or you can think of it as, well, k is 2, that means in a span of 360 degrees, you're going to fit 2 full cycles. Any way you look at it, you're going to start at 0 and end at 180 this time for one complete cycle. Notice my starting value is still 0 because I have not moved my parent function left or right. I haven't moved it up or down, so the central axis stays the same, and my a value is unchanged, so my amplitude is the same as well. So this would be the box drawing for this function. Notice that when k is 2, you're dividing your period by 2. It takes up half as much space. Instead of a full 360, it's now 180 for one complete cycle. Now this one, I have a 2 inserted here. That corresponds to a d value. That means we're moving either left or right. So my central axis is still 0 because I don't see a c value over here that would indicate moving this up or down. My amplitude, a, is still 1. So we're 1 on either side of the central axis. But I'm moving my function left 2 units. So instead of starting at 0, I'm going to start at -2. So that's how you can use a d value to figure out your starting point. We're not starting at 0, we're going left 2 from that, which is at -2. Now the period is unchanged because I don't see a k value, which would be a horizontal compression or stretch. So the period is still 360 degrees, just like the parent function, but remember, everything has been shifted to the left 2 units. So I'm starting at -2, I'm ending my cycle at 358. Now the a value is still positive, so that means I'm still opening up first instead of down. There has been no vertical reflection. Okay, so now I can figure out what the location of these key points are when I turn this into a graph. I know this point is going to have coordinates -2, 0. So we're just applying all the different transformations to the parent function still, but it's a little bit easier to draw the graph when you do it this way. Here's another example. We're going to draw the box for sine x plus 2. that corresponds to a C value. That's your vertical translations up or down. So that's going to affect your central axis. Instead of your central axis being at 0, we're going to shift it up 2 units. So now my central axis is no longer at 0, it's at 2. Now what's my amplitude? My A value is 1, which means my amplitude is 1. So what's the new maximum value and what's the new minimum value? Well, because the amplitude is 1, I'm 1 above the central axis and 1 below the central axis for my maximum and minimum values. Now, starting value. Have I moved left or right? Nope. So I'm starting at 0. What's the period? The parent function has a period of 360. Do I have a horizontal stretch or compression that would change that period? Nope. So 360 period would put me at the end of the cycle at 360. So I have my central axis, I got that from here. My amplitude, I got that from the A value, is 1, so I go up 1 and down 1. My starting value is 0. That's because my D value is 0, or you don't see it, starting at 0. And my period is 360 because the K value does not change it. So from the start to the finish, I'm increasing by 360. Lastly, the shape and direction of opening of this graph. Will it change? Nope, because A is not negative, which means that we don't have a vertical reflection. So this would be the box drawing for this function. Remember, find your central axis first. You get that from your C value. C for central axis. Next, find your maximum and minimum values by using your amplitude. Remember, A for amplitude. Then you need to find your starting value for your cycle. You get that by looking at your D value. So if you don't see a D value, that just means your starting value is unchanged. And then your period comes from looking at your K value. If you don't see a K value, that just means your period is 360 degrees, just like the parent function. If you do see a K value, divide 360 by K, and you'll get your new period. This might be helpful to write down, and you can add these little notes to your help sheet for the unit. C for central axis, A for amplitude. To find the period, you take 360 and divide by whatever your K value is. Your D value tells you the start, where you start the cycle on your x-axis. So you can feel free to pause the video and write this down on your help sheet if it helps. Now I want to walk you through this. How would we actually graph this function here? I'm going to start with the box method that I showed you how to do in the last several examples. So I start by drawing the box. My axis is -1, C for central axis. Now my amplitude, my A value, is 2. So if my amplitude is 2, I'm going to go up 2 and down 2 from the central axis. So my maximum value will be 1, and my minimum value will be -3. Now if I look at my D value, well, I don't see it in here. That means my starting value is still 0. And a K value, well, I don't see anything different in here. So that means K value is 1, which would be an unchanged period. 360 divided by 1 is still 360. So the period is 360. So I'm going to start at 0, increase by 360. So I have my start and my finish, 0 and 360. Halfway between those two values is 180. And halfway between 0 and 180 is 90. Halfway between 180 and 360 is 270. My A value is positive, so my function is still going to go up first instead of going down first. So this is the box drawing for this function. Now we're going to draw a graph. Well, let's start with putting the scale on here. I like to typically go by 30-degree increments on the x-axis. It just fits nicely with these numbers. Okay, so now we're going to take what we've done here to make this box, and we're going to make a really nice, accurate graph. What I typically do is either actually drawing the box or just kind of in my mind's eye drawing the box onto the grid. So I know horizontally it starts at 0 and ends at 360. Vertically, the highest is 1, the lowest is -3. So I can draw that box right here. And then these points, I can just draw on my box. This one's in the middle at the start, and I'm going to be at that same height at 180 and again at 360. So I can draw all those points along the central axis. The highest point will be halfway between those 2 points, and the minimum point will be halfway between these 2. Now, once you actually draw the box, you don't have to pay attention to the numbers very much. You just know these 3 points are going to be in the middle. This is going to be halfway between those, so you can just count squares. 1, 2, 3, 4, 5, 6 squares. Half of that is just go over 3 squares up to the top, over 3 squares down to the bottom. And then if you draw a nice smooth curve through those points, you've got a nice graph set to the scale of the grid. Now, we can extend this. If you want to draw more than one cycle, just draw the box again right beside the box you just drew. I can draw it to the left. I could draw another one to the right if I had more space on the grid. And I can repeat this an infinite number of times for an infinite number of cycles that I want to graph. Now let's finish this example off with domain and range. Pause the video and see if you can come up with the domain and range for this function. Here they are. There's no restrictions on x because I can keep extending this to the left and to the right. There's no limits. Range, though, there's restrictions. The lowest value of y is -3. The highest it can be is 1. So y will be anything between -3 and 1. Okay, so this function here has a lot going on. We have an a value, a k value, a d value, and a c value. I want you to pause the video and see if you can come up with the box drawing for this function, and then also use that box drawing to make an accurate graph. See if you can get some graph paper and make a scale just like the one I have on the screen so that we're using the same scale when we make our graph. So pause the video, make your box drawing, and also make a nice graph. I'll start by taking up the box drawing. The central axis is 4. The amplitude is 3. So we go up 3 from there and down 3 from the central axis. So that gives me my minimum, axis, and maximum. Next, the start point. We've moved left 60. So instead of starting at 0, I'm going to start at -60. That's left 60. My period is 360 divided by 2. Because k value is 2. So 360 divided by 2 is 180. So my period is 180. So from my start, I'm going to go up 180. That means I'm going to finish at 120. Halfway between -60 and 120 is +30. My a value was positive, so I know my graph is going to open up first and instead of down. There's no vertical reflection, in other words. So once I've figured out this drawing, I can apply that to the graph. So my box starts at -60 with a height of 1 here, goes up to 7, it ends at 120, which would be here. So this is the box. The shape of the graph inside starts in the middle, ends in the middle, it's at the middle. In between those 2 points, we're up at the maximum and down at the minimum over here. So I don't really have to look at what the values are. I can plot my points that way. Then I just have to draw a smooth curve. So there's one complete cycle of my function. But because I have lots of space on the graph, I'm going to draw more than one cycle. So you can just basically copy and paste more boxes. Now, just to have good communication here, I should be adding arrows to indicate that this function would keep going if I had more space. So here you have it. I have 3 complete cycles of this function on the graph, and I drew a very accurate graph for a hand-drawn one, but I used the box method in order to make my accurate drawing. I didn't graph the parent function first and then perform transformations to each point. I used these to quickly come up with central axis, maximum, minimum, start, finish, and which direction the graph goes. Then I used that to plot points, and I just duplicated it over and over again for the desired number of cycles. Try the domain and range now. Here it is. Because this can keep going to the left and to the right, there's no limits, there's no restrictions on x. There are restrictions on y though. The minimum is 1, the maximum is 7, so that's how we write it. In this example, we're going to write an equation for a sinusoidal function that has the following properties. We know where the central axis is located, we know what the period is, we know what the amplitude is, and we know that we have translated it 60 units to the right. So, we're going to figure out what our a, k, d, and c values are. The central axis is y equals 5. This tells me that our c value is 5. The period is 120. Well, remember, the period is equal to 360 divided by k. So if I know the period is 120, that means 360 divided by k is equal to 120. So to figure out what k is, I need to do 360 divided by 120, which is 3. So that means my k value is 3. The amplitude is 6, which tells me that my a value is 6. And the parent function has been translated 60 units to the right, which means my d value is 60. So I figured out all the values for a, k, d, and c, and now I can plug those numbers in and make my equation. So the equation of this function is y equals 6 sine, and then in brackets 3 times x minus 60 plus 5 at the end. This is the equation of the function. I got that by analyzing this information and relating it to my values for a, k, d, and c. So if you have a graph, for example, and you can figure out what these things are, then you can figure out what the equation of that function is. Like this example. Here I have a graph, and I want you to write an equation to model this graph. Now, there's some context here. We are graphing the water depth and the time of day. The time of day is given in hours past midnight, or 24-hour clock time, 6 o'clock, 12 o'clock, 18, 24. I've just rewritten these bigger so you can see it better. But 0 hours, 6, 12, 18, 24. That's the scale along the bottom. So we've got water depth, we've got time. I want you to make an equation to model this function. So remember, you need to have values for a, k, d, and c in order to make the equation. You can use the previous example as a guide. So pause the video and try this on your own to see if you can do it, and then check back in. If you need a hint, here's my hint. Start by drawing a box around one complete cycle, and if you draw the box over here, it might help you figure out amplitude, central axis, use the period to figure out your k value, and d would be your starting point. So, now that you have your hint, see if you can find the equation of this function. I can figure out the central axis is 8, so c equals 8. The amplitude, well, from 8 to 14, I'm going up 6, so the amplitude is 6. That means A is 6. The period from 0 to 12 is 12. Remember, the period is equal to 360 divided by k. So k is equal to 360 divided by the period. So 360 divided by 12 is 30. So k is 30. My d value is my starting point, starting at 0. So d is 0. So here's my equation. Y equals 6 sine of 30x plus 8. Notice I didn't have to write a d because d is 0. I didn't have to put plus 0 or minus 0 there. So this is it. In this lesson, I talked about how to draw a graph of a sinusoidal function. I talked about how to use the box method to get your starting point, and then once you know what the box looks like, you can put that onto a nice grid with a scale. Once you have done that, you'll be able to work backwards and figure out what the equation of a function is based on the graph. There's lots of practice questions. There's lots of opportunity to ask questions and get clarification, so please do so as you're working.